Are there other questions on homework, or is it going all right, or haven't started? Stuff's all right. It's not too bad. It's not too bad, I assume. All right. Let's. I just want to show you a couple more things, and then we'll talk about stuff for tests since we have tests later this week. Sound like a plan? All right. I didn't prepare anything new. I might do some new stuff on Wednesday, but that new stuff won't be on the test. So figure just talk a little bit about test stuff. Make sure that we're all on the same page with things that we've done since the last test. So let's just see if we can do a couple more problems here. Make sure that we're all on the same page. See if I can show you a couple of more things on Excel with graphing, if I remember what I need to do. So let's look at 6.7-15 to start. So the 6.7-15 has some miles per gallon for city and miles per gallon for highway based on different models of cars. So they want us to use the highway miles per gallon for Y and the city miles per gallon for X. So I'll just put city MPG here for the first column and highway miles per gallon for the second column.
What was the problem with it?
6.7-15. Yep. So we've got 20, a couple of 24s, a 20, a 21, a 20, 22, 19, 26, 24. 1, 2, 3, 4, 5, 6, 7, 8. I got them all. 5. 1, 2, 3, 4, 5, 6. Okay. Just making sure I got them all in there. And counting apparently was hard. 32, 34, 29, 29, 29, 29, 26, 32, 5, and 4. All right. So one of the things that we'll do the regression analysis here in a second, but one of the things it asks us to do is to make us plot the points and make a least squares regression line. So plotting the points in Excel is pretty straightforward. If we just go to the insert, if we go under insert, you got a whole bunch of different recommended charts. This is where your scatter plot ones are up here. It'll also connect pieces, but I don't really want to connect it. I just want a scatter plot. So we really do just want that. You could always reformat your axis here. But it started at 0. If we wanted to start at a different spot so you could see these points a little bit more spread out. All I did was just right-click on the axis. So we'll go back to do that again. I just went to the axis. Maybe. Why are you doing that? Stop it. There we go. Right-clicked on the axis to where I got the... Dr. Ruff just sneezed. The other day he had his door shut. I heard him sneeze in his office, so I sent him an email and said, "Bless you." If I click on the format axis, then I can change what my minimum and maximum are here for these. So I'm going to change this to, say, 15, just so I don't have to start at 0 there. And then you can do the same thing for the other axis, for the vertical axis. Format it. And let's say I want to make the bottom 20. Only so I can see the points a little bit more spread out. It's the only reason why I did that. One of the things that we can do in here, notice I didn't bother putting any of the titles on there. If you get your titles appropriately, it'll put them in the right spots too. I'm not worried about formatting things in Excel right now. One of the things that we can do is actually, if I remember how to do this correctly, we'll see, is actually add in, let's see if I can find it again. There's a way to add in your least squares line. I just have to remember where it is.
Mine, when I did it, there's a thing that says add chart element, and then I did trend.
The trend line is what you want, yeah. I'm just trying to remember.
Mine is in up top in the toolbar.
In the toolbar. Oh, here it is. Okay. Yeah, if I just go to this up here where it's got the little plus sign, it's not where I found it before, but thank you. With the chart elements, if I hit the little plus sign, I can click on the trend line and it'll put it in there for you.
Oh, mine doesn't have a plus sign.
Go back over here. Okay. Add chart element here. This will work.
Oh.
Yeah, you can do it there. Yep.
Where'd you go to? Chart design?
That was where it was. It was just over here where it was.
I mean, like here.
I don't know. I just clicked on the chart that was on the menu. I think you can format the trend line too, if I remember correctly. If I right-click on the trend line, I can make it. Well, you can also change whether we want it linear or a different model. You can set the intercept if you really want to. You can display the equation on here if you really want to. Which is kind of nice if we're going to check our answer here in a second anyway. Might as well display the equation. So you can also make it, oops, there should be a way to make it, you can make it solid rather than dashed. You could also put arrows on it if you really want to. There's all sorts of different things you can do. Whether or not you want to is a different question. Okay. All right. At blank there's also, for some reason I'm not finding where you can make it longer too. I think you can make it extend past the data, but that's okay. The whole reason why I wanted to do this is to show you that you can put the trend line in there. It would pop up with the equation, and then we can actually check it here when we're going to do our regression stuff. Okay. So remember how we do the regression just on this? If we go back to our data analysis, and we want to do regression, put on our Y range, and put in our X range. Like Sydney was asking at the beginning of class, notice the default is 95%. In a couple of the problems in section 7.7, they might want to change the significance level on you, so you can change that to whatever. The only thing that's really going to do is pop out a different critical value for the T statistic that we want. Okay. Output range, let's put it, okay, sorry. There you go.
You want those in
oh yeah, I probably did. That's all right. This part gives us the least squares line, and we really do see, if I would have put it in the right spot, we really do see the slope and the y-intercept that we do see up here as well. Make it a little bit bigger so you can actually see it. We actually do see the slope and the y-intercept. So we talked about finding the confidence interval for the beta and talked about how you could use that for a hypothesis test as well. Remember that for our, I'm just going to write it on the board and not on the notepad, but remember that for your alpha hat and your beta hat and your sigma squared hat, the expected value of your alpha hat really is alpha, right? And the expected value of your beta hat really is beta. So your maximum likelihood estimators that we came up with really are unbiased estimators for those particular items, right? The other piece that we wanted was the variance of each of these. This was important to talk about how we could get distributions, right? So your variance for your alpha hat was just the sigma squared over n. It's not hard to go through that particular, it's not hard to understand why that's true, because remember, what was the maximum likelihood estimator for alpha hat? It's the y bar, right? And remember, central limit theorem says what? The variance of the sample means is what? The variance of the individual pieces divided by n. That's literally just it's a straightforward application of central limit theorem. They go through in the book and derive it, but that's just a straightforward application of central limit theorem, right? Distribution of your sample means has the same mean, and the variance gets decreased by that factor of n, right? Whatever the sample size is. And remember again, the reason why this is all true is because we're assuming, remember we're doing this model that each of your y sub i's, I just want to make sure this is more of a review of this stuff as well for the test. Remember, each of your y sub i's is modeled by this alpha plus beta times x sub I minus x bar plus epsilon sub I, right? Remember that what we're assuming with all of these is that your alpha, your beta, your x sub I, all of those are constants. Well, if all the x sub i's are constants, the x bar is also constant, right? So these are all constants. The epsilon sub i's, all of these are normally distributed with mean 0 and common variance sigma squared. Right? So if we're assuming that all of these pieces are constant, all of the y sub i's have the same alpha, the same beta, depending on the x's, but the x's are constants relative to the y's, right? These are all constants. The mean of this just gets shifted to alpha, because when you add up all of these are deviations, right? When we add up all the deviations, this will be 0. So if we're looking for the expected value of y, the only thing we're going to get is the expected value of alpha, or the expected value of these alphas n times, right? So we're just going to get alpha. The expected value here is 0, right? So the expected value of each of the y sub i's is the alpha. Or not each of the y sub i's, I'm sorry. The expected value of the y bar will be just the alphas. Because when we add up these, we get 0. Okay? And the reason, and then when we do the expected value of the sum of these, well, it has to be 0. Okay? Each of these has a common variance, so when you do the sample means, this has no variance. This is constant, right? So when we do the variance of the y, each of the y sub i's, the variance is the same as the variance of the epsilons. So if we do the variance of the sample means, it's just going to be the variance over n. So the variance in the y sub i's only comes from the error, not from the others. That's why we're assuming they're constants, because the error is what's changing, not the constants. Anyway, I just wanted to mention this stuff because going back to this. The variance of your beta hats, you can go through and show, is sigma squared over the sum of your squares of your deviations of the x's. Oops, Got the square in the wrong spot, sorry. Got a little excited. The reason that is true, erase this part. The reason why the variance in your beta hat is sigma squared over the sum is because remember how we calculate the beta hat. I'm going to suppress the index stuff. But if we do the variance of your beta hats, remember that's the y sub i's times your deviations over the sum of the squares of the deviations, right? Right? Okay. Now, this relative to the y sub i's, these are constants, correct? So if I want to do the variance of the beta hat, I would pull the variance. This is just a constant as far as I go, so I can pop it out in front with a squared, right? You agree with that? If I do the variance of this whole thing, relative to the y sub i's, this is a constant, right? Because we're treating the x sub i's and the x bars as constants. So if I do the variance of this whole thing, I would pop that out as a square. The variance would go to this. These are now independent, so I can split the variance up over each one. This is a constant, so I can pop it out with a squared, right? There's a lot of me talking through that, right? But if I do the variance of the whole thing, this is a constant. When you pull a constant outside the variance, it becomes squared, right? These are all independent, so when I do the sum of the variance of the sum, it's the sum of the variances. And then inside I'll have a constant. I can pull it out in front, it'll be a squared, right? So all of that work to get to, I will get the sum of each of these times each of the variances over, this is why I got excited up there and put the extra squared to start with. That's just rewriting what I said, right? This thing on bottom is the original taking the variance of both sides and pulling out the constant. When you pull out the constant, it's squared, right? Then we have independence on the inside. So variance of the sum is the sum of the variances when it's independent. And then on the inside, I can pop out each of the constants and square them. Right? Okay? So now, each of these variances for your y sub I is just your sigma squared, right? Right? Each of those is a sigma squared, isn't it? So when each of those is sigma squared, I can pull out sigma squared out in front, because each of them is sigma squared. I can pull it out in front of this thing, right? And then I have times the sum of the squares of the deviations over the square of the sum of the squares of the deviations. So then they cancel and it gives you this. Right? So those are your individual variances of those things again. All right. Why did I want to go over this stuff again? Because we talked about it last time. I waved my hands at it a little bit last time, but I want to make sure that we're all on the same page with the idea of how these things are distributed and why the hypothesis testing and the confidence interval stuff works. This is our variance for the beta hat, right? So we also know that the distribution of these things is going to be normal to start with. The y sub I, the alpha hats, the beta hats all have to be normal because why? Well, again, This is a so the alpha is why the alpha hat, why its distribution is normal, is just central limit theorem, right? Because the alpha hat is the sample mean, and we know the distribution of the sample mean especially as n gets bigger, but it doesn't matter. As n gets bigger in general, for no matter the distribution, we get something that's approximately normal. But the y's are normal, right? The distribution of each of the y's is normal, so the distribution of the sample mean is normal, right? That's why the alpha hat is normal. The y's are normal, so the sample mean is normal, and the alpha hat is defined in terms of the sample mean. Okay? But why is the beta hat normal? Well, look at how the beta hat is defined. Again, this is just a constant relative to the y's, right? So it's a constant times the sum of constants times normal variables. Well, a constant times a normal is normal, right? Sum of normals is normal. Constant times normal is normal. So that's why the beta hat is normal, right? So alpha hat's normal, beta hat's normal. We're assuming y sub I is normal, and they're all independent of each other. Well, I'm sorry, they're not all independent of each other. Not the y's. But anyway, the alphas and the alpha, the beta, and the y sub I are all normal. The important part is that the sigma, the distribution of your sigma, will be normal. But in particular, how do we get these distributions now? Now that I know these are normal, we can standardize them, if you will, because I know what the variances are. And you can make t variables out of them. Because I can put a normal on top and a chi-squared on bottom with the sigma squared piece, right? Because we know that since all of those are normal, and like I said, I waved my hands at this a bit last time, so I want to make sure that I'm talking about a little more in general this time. We had that sum of y sub I minus alpha minus beta or beta times x minus x bar and squared, right? This is epsilon, right? We just subtracted everything over to one side. This is your epsilons, right? We squared it, so we're squaring a normal distribution. In general, I don't know much about squaring normal distributions unless I square a standard normal. When you square standard normal, what kind of distribution do you get? Chi-squared, right? To standardize this, I would need to divide inside by sigma, right? Equivalently, I could multiply this by 1 over sigma squared, right? Again, I want to go over this just a little bit more because I know I glossed over it last time. Okay? But again, I just want to go through and why is this chi-squared of it? I want to make sure that we understand where this stuff comes from. I know that we're not doing much with the computations, but I want to make sure we understand where it comes from. We got so much technology now that we lose sight of where things come from. If you don't know where it comes from, you may interpret it wrong. Okay? I'm not asking you to reproduce it. I just want to make sure you understand where it comes from. Okay? This part, again, is our errors. Our errors are all normally distributed. Typically, when we square normal, we get chi-squared, but I have to make sure it's standard normal. I don't know that this has standard deviation 1. That's why I divide it out by the sigma. Or, like I said, equivalently multiplied by the 1 over sigma squared. So I've got chi-squared of 1 on the inside for each of them, and I'm adding it up n times. Okay? All right. We said that we can rearrange this thing we're going to add and subtract an alpha hat and add and subtract a beta hat. and then put everything back together over here. Oops, that's not squared there. Squared. The reason why we did this is to try to talk about the individual distributions and why things pop up the way they do. All right, so I just added and subtracted alpha hat. That's why that's equal. Added and subtracted the beta hat times that deviation. Now, if we were to go through all the distributions, well, the middle piece of things will cancel out. Just to give you an example of why one of the middle terms, why one of the cross terms will cancel. If you take this alpha hat minus alpha and multiply it by this beta hat minus beta times the deviation, if I multiply those two cross terms together, notice you get alpha hat minus alpha, there's no i's in it, right? Beta hat minus beta, there's no i's in it. So I can move that out in front of the sum, out of the big sum, right? And then what are we summing up? Deviations from the mean. Well, what happens when you take the sum of all the possible deviations from the mean? What do you get every time? You get 0, right? That's why all those middle terms cancel out. And somehow, at some point, they're all going to cancel out either by sums of deviations are 0, or you really just do get 0 when you sum it out. Okay? But when you distribute this out, the only thing that's going to survive are the squared terms. All of the inner terms that get mixed when you square all kill each other. You get 0. Okay? Like I said, an example of one of those are just those two that were in red, right? Because you'll get the sum of deviations, which is 0 every time. So the only thing that'll survive is the sum of the squares. Now again, this has no i's in it, right? So when I add that up n times, I just get n times alpha hat minus alpha. This, the beta hat minus beta, doesn't have any i's in it either. Squared, sorry, I forgot my squared here. My beta hat minus beta doesn't have any i's in it either, so we'll get plus beta hat minus beta, sum of the squares of the deviations.
You don't have to take that times n.
No, because it's going to be a constant, just factoring out of the sum. This one's multiplied by n because I would factor it out and add up a bunch of 1s. That's just simplifying that addition here. I don't have any way to simplify this part. And then we have a plus the sum of our y sub I minus alpha hat minus beta hat, x sub I minus x bar squared.
Why is the alpha 1 squared? The very first term.
This one?
Yeah.
Because I'm squaring.
Oh.
Yeah. So I'll get the squares of each individual terms plus all those cross terms, but all the cross terms will end up being 0. All right, so let's go back over here now and compare this to what we have. This is the left-hand side, right? Right? This is the left-hand side. So on the left-hand side, I've got a 1 over sigma that I've multiplied through. So now I need to think about multiplying 1 over sigma times each of these, so 1 over sigma squared times each of these, right? So if I do 1 over sigma squared times n times alpha hat minus alpha squared, that's going to be alpha hat minus alpha squared over sigma squared over n. What did we say sigma squared over n is relative to alpha hat? This is variance, right? So I can think of this as alpha hat minus alpha over sigma over the square root of n squared, right? So now what have I divided? What have I done to alpha hat? We've subtracted its mean and divided by its Standard deviation. So we've standardized it, right? What kind of distribution did we say that alpha hat has? It's normal, right? We just converted this now to what kind of normal? Standard normal, right? And when you square standard normal, you get chi-squared. Yeah, so this is chi-squared of 1, right? Because we don't have any sum on it. It's just chi-squared of 1, right? Same thing happens over here. If I multiply by 1 over sigma squared times the beta hat minus beta times sum of the squares of the deviations, that's, if I do all the steps at once, this is beta hat minus beta over sigma over the square root of the sum of the squares of the deviations squared. Expected value of beta hat is beta. This is its standard deviation. So we've standardized it again, right? Subtracted its mean, divided it by its standard deviation. There was its variance, right? We agree? So we've standardized this, and what kind of distribution did beta hat have again? Normal, right? Square, and so this is now standard normal, square standard normal, you get chi-squared again. Yeah, so this is chi-squared of 1. Right? Okay, so then the last bit. This is all right, so I know it's not the right constant right now, but this is chi-squared. This is chi-squared. This is chi-squared. They're all quadratic forms. They're all squares of things, right? This is also a quadratic form. So if this has chi-squared, this has chi-squared, this is chi-squared, what's left over must also be chi-squared, right? And the degrees of freedom have to fill in. This total degrees of freedom was n. These takes away 2, right? So this last piece has to have a chi-squared distribution with n minus 2 degrees of freedom, right? Yeah. So this has a chi-squared with n minus 2 degrees of freedom. I still have to do the 1 over sigma squared, and this is n times sigma squared hat, right? So 1 over sigma squared hat, 1 over sigma squared times that sum so this is n times sigma squared hat over sigma squared is chi-squared of n minus 2. All right, so now think about things that we can do, if you want to think about things that we can do. Well, let's think about things that we can do now, relative to what pops up here. I now know the distribution of, well, in particular, I know the distribution of each of these pieces. This is a chi-squared, right? I know that if I take a normal and divide it by a chi-squared, I can get t distributions, right? That's how we were doing the confidence interval for the betas. But I can do the same thing for the alphas and for the alphas as well. So the way where this comes from and where this comes from for the betas, remember when you take a normal divided by the square root of a chi-squared divided by its numbers of degrees of freedom, you get a t, right? So I can take my normal distribution, beta hat minus beta over, it's standard normal, so I gotta do the square root of this thing. That's standard normal, right? Right? And then divide it by the square root of a chi squared over its numbers of degrees of freedom. That's a t. With n minus 2 degrees of freedom. Right? So far, so good with that? Standard normal divided by chi squared. Okay? Now notice in this case, this sigma squared is in the denominator of this denominator. And it's also in the denominator of this denominator, so they'll cancel. Right? So if we simplify this, we'll get beta hat minus beta over, let's see, we get square root of n times sigma hat squared over n minus 2 times the sum of the deviations squared, sum of the squares of the deviations. That gives us a t distribution. Now remember, if we want a confidence interval for beta, I would just rearrange, we would put that in between two t values and rearrange, right? We've done that before, haven't we? We've got a minus t and a plus t, and then multiply both sides and then rearrange. Remember doing those? I mean, we've talked about how to make those confidence intervals before. But we also get hypothesis tests now, right? If we want to test that the beta is not 0, well, assume that it is 0, would be that, right? And now we have a test statistic that we can do. That's where this test statistic comes from. That's where this t-stat comes from. If you go through and check it, if you take out your beta, because we're assuming the hypothesis test is beta is 0, is the null hypothesis. If you think beta is 0, you would do your beta hat, so you would do your 1.225, and you would divide it by the square root of n times sigma hat squared over n minus 2 times the sum of the squares of the deviations. Well, let's see if we can do that here. So, if you did, let's say we did the, just for argument's sake, let me redo I want to redo the regression real quick. Let's add in the residuals. So, if we do the average of the x's, and let's do, let's just copy this here. All I want to do here is calculate the deviation, so I want to do that minus this and do the sum of the squares. All right, so I'm just trying to see where we get this, where that test statistic comes from. So all I did here was just figure out what the mean of the x's is. Found the deviations and did the sum of the squares of the deviations. That's all we did there. Literally, all I want to do is just show you where this t-stat comes from. I'm not going to expect you to reproduce this either. I just want to show you where it comes from. Okay. What we're doing, I just want to show you where all this is coming from. All right. So we've got the sum of the squares of the deviations. So that's down here, right? Remember how we get the sigma hat squared? That one I do want you to be able to do. I need to take the sum of the squares of the residuals. So I did the sum of the squares of the residuals, and then you would divide it by n to get your sigma hat squared. That one I do want you to be able to do from Excel, to find the sum of the squares of the residuals and divide by n to find your sigma hat squared. But of course, notice what the numerator is. It's n times sigma hat squared, right? So I don't need to, that is the numerator. So if I divide this now, if I divide that numerator by 9 times E2, or E13 I mean, the sum of the squares of the deviations, it's not, there's 11 data points. That's where I'm getting the 9 from. I get the 0.017.
What did you take 9 times?
Oops, I got to do the square root of that too. Sorry. Say it again. 9 times E13 is where I had it. It's the sum of the squares of the deviations, wherever you have that at.
The 50.
The 50, yeah. All right, so this should be n times sigma hat squared divided by n minus 2 times the squares, the sum of the squares of the deviations. I've got to take the square root of that. So at the square root of 49, C49, D49. Right? And now, if I've done everything correctly, this is beta hat up here that I just highlighted. The 1.225, that was the slope that was calculated. Right? And if I divide that by this number we came up with, hopefully we'll get 9.1849. Hey, look at that. We did it right. This number we got here is the t-stat that I was just saying. I don't like magic coming out of computer programs without telling you where the magic's coming from. What made it magical. Not how my brain works, sorry. So that's to indulge me, even if I don't expect you to go back through it again. I do expect you to understand those common things that we've talked about before, though. You square a standard normal, you get a chi-square, right? You take a standard normal and divide it by the square root of a chi-square divided by degrees of freedom, you get a t, right? You take a chi-square over 1 degree of freedom divided by another chi-square by its degree of freedom, you get an f, right? Those kinds of relationships I do want you to know. And I really did want you to know where this thing came from. Okay? That's why I wanted to go through it again and not just say, hey, here's the magic test statistic that comes out of it. So, sorry, go ahead.
Can you click on the 9.18 one?
Yeah. So this was, this is the denominator. The E49 is the denominator. That the plus sign sitting over the top of. Right. This is this 1.1333 set. This is this. Okay. Mm-hmm. And then the beta hat I just used that and calculated out of there. Is that okay? So again, the notice here, these are our confidence intervals. You would get those bounds of those confidence intervals again by, if you think about going to your t-table You can figure out your lower and your plus and your minus t values that you would need, and then multiplying by this and adding your beta, right? Your beta hat, I mean, right? Because you would have it in between those two values and rearrange. We've talked about doing that before. It's the same as what we did for normal distribution for confidence intervals there. That's where those values come from. You have similar ideas now for your alpha, right? My alpha, this is chi-square of 1, right? So you could do another confidence interval or a t-test if you want to for your alphas, right? Because I could do alpha hat minus alpha. I know what my alpha hat is because you can calculate it. I know what its standard deviation is. You can make a t out of it, and you can do a hypothesis test and get that same t-stat out of it. So if you wanted an exercise to make sure you understood where the 1.207 came from, do a similar thing to what we just did here for the betas. Now notice in this case, we're confident that we've got a slope. Are we so confident that we have a y-intercept? Looking at that p-value, are we so confident that we have a non-zero y-intercept? With a p-value of 0.25? That's not very high, right? Notice that that's not our alpha, by the way. That's the y-intercept. The alpha is not the same as the y-intercept, because remember we use the alpha as that shift, because it's beta times xi minus x bar. So the alpha is not quite the y-intercept here, but anyway, again, like I said, if you want to just as practice, you can figure out where that 1.207 comes from, just from the stuff that we just did. You can also do, now that you know that this distribution is chi-square, you can also do confidence intervals for your sigma hat, or your sigma squared based on your sigma hat.
Sigma hat squared, that is the 8.515, or is it the next one?
It's neither. Your sigma hat would be this divided by 11.
Oh, I did.
Is that one divided by 11?
Okay.
Because your sigma hat is your sum of your residual, the sum of the squares of your residuals divided by total number of data points. But again, you could use this to figure out a confidence interval for your sigma hat, or your sigma squared, your variance. Which is kind of important if you're trying to get a handle on how bad your error is spread out. Right? All this is basically you have some sort of normal distribution for your error. So that took longer than I thought, but I really did want to make sure that I went back and talked about that stuff that we did on Friday. Okay. Because I really waved my hands out of it on Friday. I didn't wave my hands out nearly as bad today. Okay. All right, so we'll do more talking about test stuff next time. But and then you pretty much guess what the test is going to be over. We've done hypothesis testing, right? So the various hypothesis tests that we've done. The stuff with ANOVA and the stuff with regression, I do expect you to be able to use Excel on it and not doing it by hand. Okay. So being able to do the one-tail ANOVA, the two-tail ANOVA, and the regression stuff that we've talked about here.
Will it be mainly on Excel?
Yeah, that part will be mainly on Excel, yeah. The other hypothesis test stuff, you need to make sure that you know your test statistic stuff. All right. All right. We'll see you next time. Oof. Some of you I'll see tomorrow.